Okay, well, here's an interesting, entertaining thing for the beginning of the day. So some of you have heard this before, that I see a special kind of chiropractor. So you see this kind of thing? It's going to give me a bigger version of that picture, maybe not. You know, this needle right behind the ear thing here. So you know how doctors call chiropractors quacks? Chiropractors call this type of chiropractic a quack. It's called Atlas orthogonal. Now the thing is I'm like totally sold on this. I've been going to chiropractors most of my life, and one thing I like about this is that if you've ever been to a chiropractor, a lot of times you go in, they have you go like twice a week at first, and they want you on some sort of maintenance thing for the rest of your life, right? So the first time I met this guy was in 2014. I broke my back years and years ago. So I've had a long history of back problems, but I would have flare-ups. And I would be like out of commission for like 3 months. And I'm a golfer. And one of my buddies from the golf course said, hey, you got to go meet this friend of mine. And the funny thing is the way he sold this guy is he's like, yeah, so here's the story. I was once dating this girl. This chiropractor stole the girl from me. And I'm still recommending people go and see him. He's that good. So you go in and he hooks you up to this crazy machine. It looks like this. And well, first he takes all these x-rays. It's all like geometry stuff. But the idea is that it's your very top bone in your head is called the atlas. And your head sits on top of the atlas. And when your atlas is just slightly off, that means your head is not quite on straight. So your eye line is a little bit off. Well, our natural inclination is to level our eye line. So if our head's, 1 degree off, let's say, even a fraction of a degree off, we turn our head to level it, which pulls our shoulder up, which pulls our back up, which pulls our hip up. Everything else gets out of whack because this wasn't quite on straight. Now, this torture device that looks like it's just a sound wave. It doesn't actually even touch you. Yeah, it's like, okay, this thing, he does his best not to pierce through the other side.
What happens is like they push the whole needle in and then like adjust the bone.
No, it looks like that. It looks like that, but like from a going through the treatment perspective, bzz, you just experienced it. That's it. You don't even you kind of feel a little something like like a vibration, whatever. But something is happening. You can watch videos and stuff where it actually shows them having it on a MRI or something like that that's showing it happen. You see the thing move, the bone move from the sound wave hitting it. But you can tell like blood like rushes whatever was causing the thing. But it's very interesting that it's helped me so much historically. But I went and saw this guy this morning because my back's been killing me lately. I've been putting myself into weird positions, checking under beds and stuff. But he said my atlas was 11 degrees off. So, yeah, but what I really like about this guy is the first time I went and saw him, I was really messed up. I was like all hunched over and stuff like that. So he saw me once. He said, okay, I want to see you again in 2 days. Came back 2 days later. He said, okay, I want to see you in a week. Came back in a week. He said, everything looks pretty good. Why don't I see you again in 1 week? We're only going to do something if it seems off. Came back a week later. He said, you look good. I'm not even going to touch you. Not going to charge you. Call me when your back hurts. Like, that's not great for your bottom line, right? Okay, but isn't that the kind of like healthcare provider you want? Somebody's like, so.
Well, and then as you're walking out, he shoots you in the back with a BB. You go, my back. And he's like, all right, come back.
Oh, your back hurts, huh? Yeah, so this place is called Atlas Orthogonal. It's out in Tosa, Brookfield area. Highly recommend it. It's, yeah, this is actually the guy. This is.
I was hoping it was the guy in the other picture.
Oh. And actually, I do have a picture of this. He's a little bit younger in this one, but having him, Mr. Gonzalez, has been on this machine. Legit. There's initial pictures of Mr. Gonzalez on there where, like, I'm posing him beforehand. So you're thinking, oh, this is just before the chiropractor came in. No, we got this guy giving the thumbs up while he's actually got Mr. Gonzalez on the machine. It's pretty funny. But yeah, in any case, I thought that was a interesting pluck because it's, I went in pretty messed up today, and he's like, did it once. He said, I think you're going to do okay with this. Just call me when your back hurts after one visit. So I scheduled for next week because I just wanted the extra checkup just in case. You don't even want to see me back. I said, okay, you cancel that if you feel okay. So, okay. So homework for today was to create our variable environment. Last time we talked a lot about the idea of super and whether or not the idea of a parent or whatever exists at a higher level always, right? Do we always have an instance? And we talked through the idea of, do we do it on demand? Do we do it initially? All right. So I think we decided that we need to have a variable environment that has our baseline object in it, right? And whenever we create a instance of a class, now remind me on the homework, were we actually creating, I don't think we were creating instances yet, right? We're just creating programs.
Base object class.
And yeah, the class expression, not the instance of a class expression. Is that accurate? Here we go. So create an environment that stores our initial object, create a start of our interpreter that allows for the creation of a solution, which is like our program, and the creation of a class, so our very first type of expression by our, we should be able to look things up in our environment. Now we can decide how we want our environment to ultimately work. What do we think? If we think about our environment for a few minutes, variable environments work by thinking about what is the most local scope of a, we kind of have this, let's call this guy variable scope. So variables resolve to their most local definition, something like that. Now, what do we call a local definition of a variable? We call it a scope, right? Or a local place where a variable can exist. So what are examples of scopes? Well, we have the global scope, which governs the entire program. Then we have a scope per function. That's a place where we've seen scopes before. So every function that we have has its own local scope, like when we're dealing with our lambda expressions. The parameters, those variable bindings, those created a local scope, right? So a scope per function. We have a scope per class. Is that an accurate statement? So in our new language here, we have a solution, a program that's made up of initially class definitions that are then supported within the scope. So we have this global scope of our program. Each of those classes has their own scope. So can we have a variable named A in one class and another variable named A in another class? A field? Yeah, we can have fields that have the same name between classes because those guys live in different scopes. Okay? So when we think about our variable environment, I'm guessing many of you, so if you notice the pattern we've been going through more recently is I've been having you solve problems with the hope maybe you think about it a little bit more generically, but chances are most of you probably followed the extend DNV and the normal jazz we did up to this point, right? Okay, well, I want to kind of reinvent that a little bit in our head. So with that in mind, when does a new scope get born? Or what is our variable environment in a modern programming language? If we were to define variable environments, so I'll call this modern variable environments. What are these guys? How would you represent that? Okay, well, yeah, we might have types. I'm thinking about the organization of the variable environment, kind of what we're talking about here. would we say, is it fair to say it's a collection of scopes?
Yeah.
Now, do some scopes disappear and other scopes stick around? So when does our global scope come into existence and when does it disappear?
Comes in at the beginning of the program and then goes away over time.
Yeah, so when the program ends, the whole program ends, the global scope's gone, it comes into existence at the beginning of our program. So when we say that's the most global scope is the global scope, whatever we decide to call it. All right. And then what happens as we come from our global scope and all of a sudden we define a function that has a more local scope. The idea is variables always resolve to the most local definition, right? So what kind of collection of scopes? Where a scope is a collection of name value pairs. What kind of collection are we dealing with? If we think about it in terms of data structures, how might a scope be organized? Go ahead.
Is it tree?
Tell me more about why you think it should be a tree. I don't want to say no yet if you have a good explanation.
Well, I guess you could have like functions, you have multiple functions, and in each one of those you could have, a loop or some other kind of like, if statement or something like that that would have its own.
When does the scope for a function first get born and when does it go away?
I guess when it's run.
So when it first executes?
Yeah.
So when it comes into existence. So does the existence of more than one function mean that we have the existence of more than one scope with those functions, or only when the function is actually executed?
I guess it would just be during execution.
Will we ever call more than one function at the same time?
Yeah, I was just going to say, if you have two functions running at the same time, you have both scopes. However, if you're only executing one function at a time, it should close out that.
Let's draw some pictures and let's do a little universe crossover with operating systems. So we have our program. All right. And we're all cool with our program having his own scope. That one's an easy one, right? We get that global scope associated with our program. Everybody's cool with that? Okay. Now, actually, I guess I can steal this whole thing. We have method 1, and he has his own scope, but only when method 1 gets called. All right, so we're going to say these guys are all currently being executed, right? So here, we'll put that in green. This guy's being executed, put that in green. All right, and maybe method 1 then makes a call to method 2. Now, method 1, method 2, these guys were defined at some other point in time in a text document, right? But not until we actually called it did the scope that belongs to method 2 become the most local scope in this thread of execution. Okay? So we have our program, which usually runs, and we'll start connecting this to the your OS stuff. You've talked about threads in OS, right?
Mm-hmm.
All right, so this is your main thread. So typically in modern operating systems, when you start a program, it starts running in its own, it usually gets a process ID, but typically it also then generates a more local main thread. And this has to do with CPU scheduling because otherwise if you have a process that forks a bunch of child processes, then that guy naturally gets more CPU time. Where if he is spawning child threads, then those children all share the same CPU time with the main thread. It's more fair. That way you don't have one program that's taking over the operating system by just saying, well, I started off as 1 and now I'm 30 simultaneously running processes getting 30 times the CPU time of everybody else. It's like, nope. Now you 30 little minions are all competing for the same amount of CPU time if you operate as threads. Okay, so we have our main thread here that the program runs on, and then when our normal traditional programs are, we have our main method. So here, this guy maybe is main, and then the main method calls off to another method somewhere. So the main method is kind of put on hold. Now that doesn't mean his scope goes away; he's still active, right? But he makes a call to this other method, who now has a scope, right? And this is all happening inside of that main thread. Go in the outer limits here. All right, so these scopes, so this is currently our most local scope. And that guy shadows this more global scope, which shadows this more global scope. So if I have a variable named A here, and a variable named A here, and a variable named A here, and I'm in this method, and I reference a variable named A, it's going to find the definition here. Now, if I have a variable B here and a variable B up here, but not a variable B here, and I reference B inside of this guy, it'll find it in one scope up, right? It'll look locally, say, oh, didn't find him here, but I have another place to check. So we'll check and find it there. Similarly, if we have to go up and find a variable in our global scope, that's where we'll find it as well. Okay, but all this is happening linearly inside of a single thread. All right. Now, let's say within main, we spawn off a child thread. And typically when we spawn off a child thread, that's attached to let's just say a method call. We're going to run this method in its own thread. All right. What's the advantage of having this method? So we'll call this guy method 1 and this method 2. What's the advantage of having one run in main thread and one run in child thread? Running at the same time, or as if they're running at the same time. If we're operating on a single core CPU, only one thing can run at once, right? So they're getting scheduled as if they're running at the same time, but there isn't necessarily a guarantee that they are running at the same time. Now, on a multi-core CPU, which is common today, right? It is possible for two threads to run on separate cores. Traditionally, two threads that belong to the same program would have to be written explicitly to be allowed to run on separate cores, minus some special algorithm type stuff, because one thing we have is, well, you have several different things when you're dealing with multiple threads, but one thing is we do have a chicken or the egg problem where if maybe one thread is reliant on another thread finishing before it can continue or before it can do its next step. So we need to have some way of having these guys talk to each other. It used to be called inter-process communication, IPC. More recently, it's inter-thread communication, but we still call it IPC. Yeah.
So that brings me to because a lot of programs don't actually support multi-threading in that respect, so they just run on their single thread.
Well, you mean most programs that people write, they don't necessarily spawn off other threads?
Correct.
That's probably a true statement.
So then if you're using some kind of a wait function, it's waiting for something to happen. Is it just round robining back to that like constantly? Or is it just spawning another thread? Because if it's
well, you wouldn't wait in a program that typically wait is, well, if you're talking in Java speech, also C#, wait is waiting for some signal from a thread to notify you.
If
It's
working on a single thread, how can you do a wait?
well, in that case, you're not waiting.
You're not.
Yeah, you wouldn't use a wait. It would be kind of an incompatible thing.
Okay.
You, in that situation, you're kind of wanting to put some sort of timer up so you delay 3 seconds for,
Whatever.
yeah, which is usually not a great programming practice to just randomly have delays. Years and years and years ago, people used to have busy wait loops. I think I've used the example in some of my programming classes before with an old Double Dragon game that was made for DOS, where I had it on a very old machine and it ran great. But then years later, we got a much newer machine that would be elderly by today's standards, right? but the game was unplayable because all the delays for like when monsters came out, when the next boss came out and some of that was all based on like busy wait for loops. Well, those loops ran a lot quicker on newer hardware. So you had the whole level out like right at the very beginning. Your guy's sitting on screen one and the whole thing, everybody's there. It was a platformer. So, yeah, busy wait loops, bad idea. Okay. Same thing, saying wait for some number of seconds. That's probably a more reasonable idea because at least seconds we can say this is maybe related to the user. But kind of event-driven programming has been the solution to that rather than waiting some fixed amount of time. We see like press any key to continue, rather than, we'll give you a 4-second pause and you're sitting there. This is like the longest 4 seconds of my life. We don't like that. So typically it's in a single threaded application, you probably would not. The wait goes hand in hand with a signal from another thread.
Right.
And you wouldn't have threads raising signals. This is did you guys talk about interprocess communication in the OS class? All right, so when you have multiple threads or multiple processes, either one, this guy is running in its own thread, this guy's running in his own thread. These guys now have deviations, right? This scope and this scope live in like almost different dimensions. They're not related to each other, all right? And if we take away the word thread, which thread means kind of a more modern thing, and we literally think about these guys as almost separate programs, separate processes. They're in their own little worlds, right? And these guys are, for all intents and purposes, from our perspective, running at the same time. Whether they're actually running at the same time or they're just being intertwined with each other, scheduled on the CPU as if they're running at the same time. The point is that right now, this method right here is being blocked by this method call. He's on hold because this method has been called. And we won't get back to the next line of main until we get to that, the end of this method. Once this method ends, then we can continue on with main. But when main spawned off the thread for method 2, that was a non-blocking call. He kind of created a new Christian worldview, I think. So he created a new method. This is creation, people. Okay, so created a new method, even makes noise. All right, and then says, go off and do my bidding. And then I'll sit here and keep doing my thing. This is how web servers work, right? How does Apache web server, work? I mean, does Google only allow one person to connect at once? You have to wait till their search is done before, no, right? Incoming connection, Google web server picks up the phone, hello, certain IP address, what does he do? Go deal with this guy's search. Back to listen on the phone. Go deal with this guy's search. Back to listen on the phone. That's what the web server does, right? He listens for incoming connections, then creates a new thread of execution. Usually for high performance things like that, they're using thread pools. So he grabs he has a pool of unused workers. Says, you, deal with them. Hands them the phone, run down the street, go deal with them. Then he goes back to doing his thing. All right, so that's how modern systems work. Go ahead.
So kind of to compare when I'm thinking of, like with a database transaction, only one person can change something at a time. If you wanted to change something in the main thread in that upper scope, could you do that from both threads at the same time?
Yep, hence the need for a semaphore.
Okay.
Right? So if your OS class talking about semaphores, all right, so yep.
Okay.
You got two threads that are potentially running at the same time, and they both are vying for the same resource, and only one guy can have that resource at once, let's say. You need something to protect that resource. And what makes semaphore special? What's special about semaphores that makes them better than your own internal homegrown way of protecting it? A lock, yeah. They run as if they're atomic, right? It's an atomic execution. Whether they're actually atomic or not isn't important. It's at the low-level language level. They execute on the CPU as if it's a single instruction. Therefore, nothing can squeeze in. in between. You know, if you have 3 instructions that equal a sem up or a sem down, a semaphore is effectively an integer.
Yeah.
You know, it's just a counter, but it's a counter that increments or decrements atomically. There is no, it's like on the way during the incrementation, this guy slid in and started changing my database, right? No, you increment it, single instruction. Now you're in the critical section, which is the code that you want to execute while nobody else can execute it, right? Doing your crap, and then as soon as you're done, you decrement, release the resource. You finished your thing, right? Now, human nature would be to have your entire program in the critical section. Like, my resource, I'm going to run for an hour and a half, and then I'll release the database. But usually you only you read functions from a database. They don't need to be protected. But when you've got multiple threads potentially updating a record, yeah, you might want to have that guy be protected. But that's not just good enough. All you're doing there is saying that one guy can't update the database at the same time. That doesn't mean as soon as this guy's done updating and releases the resource, this other guy can't come in and update it and make a change that overwrites this guy's change, and nobody knows, right? It's still whoever changed it last is going to be the final result. So these guys might need to now have communication among each other. So this method that's running inside of one thread and this method that's running inside of another thread, these guys might need to talk to each other in order to kind of, get a game plan together, right? Maybe the quarterback, he's going to talk to 2 of his receivers. One of them's going for the end zone. One of them's going to go out and cut across. He's got 2 options at this point. If we just say, okay, I need one of you to go to the end zone and the other one to cut across, and both of them decide to go to the end zone, then we have a problem, right? So they have to have a game plan, and one of these guys lets them know kind of what's going to happen, or like, okay, I just caught the pass. Therefore, the guy who's in the end zone maybe doesn't need to be ready for the pass anymore. It's not coming. Pass has been thrown. We're past the line of scrimmage. You got to do the whole backward scoop thing, right? The trick plays. It's not going to happen anymore, right? Did the Packers forgot to play yesterday, right?
Forgot to?
Yeah, they got blown out. I didn't watch the game, but it
Okay.
did not look like a close game.
Okay.
It was like 37-8 or something. It wasn't a close game. Well, they were supposed to lose, I think, by record. I think the other team was 9-1, and the Packers were 8-2. But looks like maybe there's a little bit more distance between those teams than was seemingly going into it. But in any case, that was just the football analogy bringing that up. But you kind of see the point is that a semaphore does one job, but it doesn't solve all the problems. These guys still need to potentially communicate with each other, and that's where we have, like, maybe this guy says, okay, I just finished my task. I updated record B. This guy might say, okay, well, I was getting ready to update record B. I won't do that now because you've already done that, whatever. So you might need some communication between these guys. All right, that makes some sense from an OS. I don't want to go too far down the OS track, but that's the purpose of these inter-process communication things, right? Whether it's inter-thread or inter-process, same thing. We have ways of protecting resources from having too many processes access them at the same time, but that doesn't mean that they will never get access to the resource. We also need to have communication channels between processes, and that can come in the form of signals. Signals are kind of the simple way of doing it, where you just kind of say, hey, yo, I'm done. Just waving, signaling somebody. There's other things where you need to get data over to the other guy, right? Signals, you can have simple signals, right? Just like in, baseball, and the coach gives you like the signal to steal. You can see the guy down there, he's got all these, tip of the hat and all this stuff. So there's like, 90 different hand gestures that he might do, and each one means something, right? Well, you can have 90 different signals that mean something. So like, this guy means hi. Okay, this guy means, thumbs up, good, we're good. Let's use those 2 as the example. Those are both signals. They don't really carry data, but have meaning in and of themselves. That's a signal. But now, what if I need to give you some information? I just made some updates of stuff, and I need you to have the person's new account balance. after me doing my thing. Okay, well, I guess you can come up with some sort of Morse code-y type of signal thing where, I'm going to transfer the account balance to you through a gesture of dance. Because, you're just doing all this choreography and stuff like that. Maybe not the best way of doing it. So what do we have? We have pipes. We have shared memory is a pretty popular thing where, we say, look, I'm going to go ahead and store the value over here. Then I'm going to signal you. Telling you to go check it. Okay, so you get the signal, but after I hid the goods, right? And then you go check the shared memory. So shared memory would be a more global scope that's shared among two processes. Make sense? All right, so we see how, again, this kind of falls into that category of the grand ideas of computer science, right? We're talking about language theory here. We're very clearly talking about how programming languages are working. And at the same time, we see direct relationships with operating systems, right? And can you take it a little bit farther and realize there's probably some pretty close, we also talked about computer organization and architecture in here, that low-level language and how that translates on the CPU, how the CPU runs, handles an individual process. So all these things are interrelated. Okay, so with this in mind, the question had come up, what if two methods that each have their own scope are technically running at the same time? Well, this scope and this scope both exist at the same time, but these guys kind of live in different universes. We can't access each other's scope directly. Does that make sense? All right, so this guy can't get to this scope because they kind of exist at the exact same time. And they're updating at the exact same time, and we're purposely keeping these guys separated from each other. Now, through some communication, this is again back at the operating system level, this guy could ask this guy for one of his values, but he wouldn't be getting that through traditional variable resolution. He wouldn't be going through the normal variable environment scope model. He would be, calling somebody up and say, "Oh, how old was Frank again?" that type of thing. All right. So these guys do exist completely separate. It doesn't break our scope model. So when these two guys split here, depending on your multi-threading or multi-process model, a couple different things could have happened. If you look at the multi-process model, you guys looked at the fork system call in OS for processes before multi-threads. So the multi-process model, so that was called the old school but potentially problematic version of multi-processes, and it's where GitHub came up with the fork command. You fork a copy. All right, so the idea is that right in here, main, he created a new thread and told him to do this stuff. So this is the new child worker over here working. And then right after that, he called this method, which puts this dude on hold while this method's off doing his thing. So this method's running on the main thread, so only one thing can be executing on the main thread at once. But right before he blocked himself, he spawned off a little worker bee to come over here and do something else. Now, if you do this in multi-threading, this guy is happening inside of the same CPU time space as your main thread. They share the same CPU, but the historical way of doing this would have been this. We would have called the fork system command, and this is where in an OS class things always start getting a little giggly, because we're actually forking a child, and then things go down from there pretty quickly. But we call the fork command, and what does the fork command do? It actually creates a duplicate. It clones the current situation, the whole situation. So when a program forks, you get a whole nother program that is a copy of that program. Complete duplicate. Program counter and all. In fact, they have to then follow that up with an if statement. Am I the original or am I the clone? Because they're using the same body of code. They are duplicates of each other. So the very next thing says, usually fork. This guy would have something like, int PID is equal to fork in C, something along these lines. The fork system call does the magic of cloning, right? But then he returns the process ID of the clone. PID equal 0. I'm the original. PID equal, or let's say not equal 0. I'm the clone. I.e., we might say modernly, the new thread. Make sense? But now new threads only hold the code that you want them to execute. Where back then, a new process was literally a duplicate of the old process. A full duplicate of the old process. It's still on line 17 of the code, and then they go to line 18, and they both ask the same question. What is my PID? If one of them comes back as 0, I should keep doing the parent stuff. If the other one comes back as something other than 0, I'm the child, I'm the clone, I have my own task to do. And that's what I'm going to go ahead and do. But what's important here is now you have 2 copies of the global scope, 2 copies of the scope associated with main. And now you have these new scopes that were born out of this. Let's just do this for our example here. So if this guy was to modify this global variable here, he's modifying the global scope associated with this cloned program. It will not have an effect on this program over here. So you're getting a second copy of that variable environment. So having 2 programs run at the same time typically means that you have now cloned your variable environments and they are no longer, they're in different dimensions. Does that make some sense? Go ahead, you have a question, Jack?
Yeah, I guess I was just wondering with fork, so with like threading, they all kind of split the CPU time, but like if you fork the process, can you just like get twice as much CPU time?
Yeah, that's what I was mentioning earlier, right? Yeah, and then if you keep forking multiple times, you get more than twice as much CPU time. So you can, it's actually one of the early ways of, let's call it a more local denial of service attack. Write an infinite loop that just keeps forking. First of all, you're going to run out of unique process IDs. It is an absolutely destructive attack. I'm not even kidding. You can write 4 lines of code and bring a whole OS down because you can run out of process IDs. Where no longer the OS can no longer create new processes. And what does that mean? The system admin can't actually get into the system and open up a terminal to kill off the original process. They can't stop it.
Well, it would grow exponentially, wouldn't it?
Yep.
Because each fork is going to start forking.
Yep. You can bring a system down. You can bring a system down really quick. Really quick. That's why threads are a lot safer. Because, hey, you want to run out of your unique number of threads within your own program, you're only hurting yourself. Because all of a sudden you start getting to the point where you're sharing CPU time with 4 zillion threads.
I was going to say, yeah, you got 32 branches.
And you're constantly context switching. You talk about context switching in OS? I'm getting a nod from probably the good student. I'm getting an eye. Huh? You're nodding, good students.
Look, it has been 2 years since I took that class.
That shouldn't matter. Context switching is probably the most important computer science concept that comes out of OS.
I need to hear context.
Context switching is the idea of when a program loads onto the CPU, it unpacks its bags. Okay, so our CPUs can run multiple programs. That's the idea of multitasking today. So it gets onto the CPU, it unpacks its bags, it runs for some period of time until he either has run out of runway. CPU says your time is up. Actually, the CPU wouldn't say that. The process manager CPU manager would say that. Or he does I/O. And I/O is an interruptible thing. So either way, when it's your time to get off the CPU, you might not be done. So what do? You pack all your bags. You remember all of your register values and all that crap, and you get out of Dodge. And then you go do what you're going to do, and you go and get back in line for the CPU. Well, that's a context switch. It takes time to unpack bags and to pack bags. That makes sense? So every single time a new process gets onto the CPU, that takes time. That's time that your CPU isn't actually accomplishing something. Your CPU is just switching users, switching programs. That makes sense? And one of the goals of an operating system is for our CPU to be as busy as it can be, as close to 100% of the time as it can be. The reality is we hit something like 8 to 9% of the time in the peak performance. Unless you're playing a game or something like that. Usually if you're running a single program, you can get pretty good CPU utilization, but that isn't your common task on most computers. But context switching is something that's necessary for multi-program operating systems. If you want to run email and your web browser at the same time, context switching will have to happen behind the scenes, right? So we want that. But at the same time, you want to minimize the amount of context switching while still faking out the end user. That's the goal of the OS, is to make sure we believe everything's happening at the same time, whether it actually is or not. And that's a combination of multi-cores and fast processors. Like, look, if I can do 13 things seemingly at the same time, but I do them so fast that you don't notice, that's as good as being at the same time. That makes sense? Context switching is a core tenet of operating systems.
Flash playing tennis with himself.
Yeah, something like that. As long as you think the match is real.
Just as a note of curiosity, do modern OSs tend to have kind of safety locks in place to prevent this kind of attack?
Oh, sure.
Okay.
Sure. Usually a process was going to have some sort of limit on the number of a user run processes.
Right.
The second you start running something as administrator, some of those things go out the window. Right? So ever notice when you're on a Windows machine, or Windows is probably the most common in here, but it says you must run this as administrator, or if you're on a Mac and you have to run some command as sudo. Yeah, so super user do, you're doing that as the super user. Make sense? So those are, you're kind of playing with fire at that point. You're saying, look, I realize that I'm now taking full control. And that comes with some, with great power comes great responsibility type thing, right? But stuff can get real pretty quickly. So what I want you to do for next class, new variable environment, which should not change your assignment that was due for today, because you're just going to replace your old variable environment with a new variable environment. We want to implement variable environment as a stack of scopes, where a scope is a collection of name value pairs. You can implement that however you want. If you want to have that as your extend DNV or something like that, you can. If you want to just run it as a list of two lists, collect it like a dictionary, it's fine too. It doesn't matter. I don't care what that looks like, because just write your implementation to make it work. So a scope is going to be a collection of those, but the idea is that when we enter a new method, etc., that would create a new scope, we can push a new scope onto the top of the stack and add variables to that scope. And when the method / etc. ends, popping that scope from the stack returns us to the state prior to the method / etc. existing. Make sense? Go ahead.
When we push a new scope onto the stack, should it be a copy of our previous scope with added stuff?
No,
No.
no.
So
A
Dave
scope
should
is a
be-
fresh scope, but it's your old scope is still on the stack.
Right. So Dave should be all the way at
Yeah.
the bottom. And
So
not
apply ENV will always check the scope at the top first, but will continue down the stack of scopes when resolving variables. So we don't need a copy. We haven't lost the old scope.
Okay.
The old scope's still there. We've just put a fresh scope on top of it. And we might be inside of a method. And if we're looking for variable A and it's found inside this more local scope, great, we'll resolve it. If we're looking for B, we'll check the local scope. If we can't find it there, we'll pop. Probably have to work with a copy of our environment there because we don't want to destroy our environment, right? And then check the next scope down. That make sense? All right, so your homework should still function from the what was due today, but the way you implement your environment and how you apply ENV will change. Make sense? What I'm asking you to do for next class? So we're just changing the data structure, we're changing the approach, we're changing the functionality of our the features of our variable environment to now allow us to subdivide it into scopes. Cool? Questions, comments, concerns, bribes? All right, I will see everybody on Wednesday.
So